Good morning, everyone. My name is Bo Wang, and I'm a PhD student from Penn State working with Dr. Longjing Chen. And it's my great pleasure to be here for the third time, and I'm very lucky to give an oral presentation for my work about the domain structures in 111-oriented tetragonal ferroelectric thin films. And so we're starting from something we're familiar with. So for the perovskite 001-oriented ferroelectrics, I think Dr. Ouyang just gave a very comprehensive review. So you have 6 different orientation of the domains, which give you 3 types of twinning structures, including the 180 domain walls, C+, C- domain structures, and the AC domain structures, and the A1, A2 domain structures. And because of the implant symmetry, and so we can use the implant misfit string to tune between these domain structures. For example, the compressive string will favor this antiparallel polarization state, while the tensile string will favor the implant polarization state, while a small string will favor these AC domain structures. And things got more interesting for 111-oriented films. For example, here I plot the still the 6 tetragonal orientation, but with a 111 orientation. And in this case, all of the 6 polarization directions, they're actually degenerating in terms of energy. And because of that, there are 2 types of twinning structures. We can make a link from the 001 to 111. So, for example, starting with A1, A2 domain structure like this, and we make a cut along the 111 direction, we can see this is the first type of domain structure for 111 systems, which has a out of net polarization along the out of plane. And looking at the sideways, the domain wall is tilted, the 90-degree domain walls, they are tilted. And the other one is when we're making the cut perpendicular to these 90-degree domain walls. And this will give us zero net polarization along the out of plane because of the up and down polarization configuration. And looking at the sideways, the domain wall, 90-degree domain walls, they are perpendicular to the substrate. And we give a name for the first and second 2 types of twinning structures as type 1 and type 2. And type 1 is polar, type 2 is nonpolar. Actually, this has been first reported a long time ago by Romanov and his co-authors. So there are quite a lot of experimental studies recently on these 111-oriented thin films. And the domain structures are much more complicated than the previous twinning structures. For example, Dr. Lane Martin's group has a nice series work on 111-oriented PZT systems. So this is what they discovered. One is one polar domain structures with 3 polarization variants, and they form these 120-degree patterns, like a herringbone structure. And the other one is a pattern with a 60-degree angles, and this one has a 0 net polarization along the outer plane because of one of the polarization is pointing down, and this is like half of the volume fraction. The other 2 takes a quarter each. And they discovered that by controlling the volume fraction between this polar state and this nonpolar state, they can tune the switched polarization and create these multi-level storage systems. And another example is from this work, people found that even for this polar state, we can form 3-band structures, and also to create 1-band structures. And they compare the for example, here's the fatigue properties between these 2 states. And they show that both of the cases, they have better fatigue properties than the 001-oriented films. And for these 3-band domain structures, there are some reports saying using this current AFM, they see the junctions between the two bands has actually a large local conductivity, which indicates they may have formed some charged domain wall, charged junction vertices. And also there are TEM studies that report domain structure evolution with the increase of the thickness for the PZT films. For example, in this very thin film case, they saw a mixture between the polar and nonpolar two types domain structure, while in the thick film, it becomes all the polar type 1 twinning structures. And most of these works, they are PZT systems, and there are also new reports on BTO systems, which they are all tetragonal systems, and they show beautiful domain structures and new properties. So the motivation for us is that most of the previous studies are experimental, while the theoretical studies, they are limited to like single domain state because of the size limitation. So we're thinking of to use our phase field method to study a large mesoscale with this 3D thin film setup. For example, here is we're studying like half micron size with a fixed thickness of 20 nanometers. And in this work, we do not play the game with temperature and misfit strain, so we just fix at room temperature and zero misfit strain. What we play with is first is the initial polarization state. So we can either start from random nodes with all the polarization directions, or we can apply a built-in bias to select few of them. For example, if you apply autoplane electric field, we can select only these three polarization variants. And the second thing we can control is the electric boundary condition on the film surface. So we're studying the two extreme case when the polarization is perfectly screened, which is a short circuit boundary condition, also when the polarization is partially screened or non-screened is an open circuit boundary condition. Our third thing we can manipulate is to model a scanning PFM tip, which we can apply mechanical force locally or electric bias locally. And the path of the tip is totally programmable, so we can really do a scanning tip modeling. So all of these good things, actually, they have been implemented in our phase field software called MuPro, and is commercialized and developed from our group. So we started from the first part, which I'm using the lead tightening system as a model system. So if we start from the 6 polarization variants, that's what we got as the equilibrium state. The first look is quite messy, these domain structures. We have all of the 6 polarization vectors, and we have some local ordering. For example, here, this type of twinning is the type 1 twinning, which I showed in the very first slides. They have an overall polarization direction along one of these red directions, so the 111 crystallography families. And the other type of twinning structure is this type 2, which has one up and one down, so 0 out-of-plane polarization. And this type of twinning, they have a polarization direction along one of the 6 blue directions, which is 110 crystallography families. And experimentally, this is what they see when they first, the as-ground state of the thin film. That is also looks quite messy with, we can see some local fringe, but overall they do not show a very regular pattern. And the second example, when we apply electric field to pull up this system, so we only have these 3 polarization directions, and this is what we got at equilibrium. So we get a much nicer look domain structures, which has 3 types of domain bundles. For example, here is the type 1 state, like the previous case, and we got the other 2 energetically equivalent twinning structures. All of them, they show the locally polar structures. And this has also been reported in experiments that they also see the coexistence of these three types of domain bundles. And they also see this 120-degree domain walls between the neighboring two bundles. A third case is when there's no net polarization autoplane, so we can apply an in-plane bias electric field to screen out the other domain variants. And this is what we got also at equilibrium. So these domain structures change significantly than the previous two because the local twinning structures, they are actually non-polar in this case because we're using so the screening is not perfect, so it's kind of an open circuit condition. So we have both autoplane and in-plane domain structures. And they are consisting of two types of the type 2 nonpolar twinning structures. And the angles between these neighboring bundles shows a 60-degree feature, and this is also consistent with the previous experimental results. And we can do furthermore by screening out the 4 of the polarization, but only left 2 of them. And this gives us stripe domain structures, and with the polar twinning structure, and this has also been observed by TEM studies. A final possible domain structure is when we have one up and one down. But it turns out that this initial setup does not give me a perfect up and down twinning domain structures, but it will relax to a more complex domain structures. But look closely, we can see that this is actually a mixture of 2 types, which has this wider domain patterns with the type 1 polar twinning structure, while there's locally some up and down, so nonpolar domain structures. And what's more amazing that this is also quite consistent with the experiments. When the film is very thin, they also see this combination of type 1 polar and type 2 nonpolar twinnings. So the question is, we have all these different beautiful domain structures. Is that possible to convert between each 2 of them? So the first thing we try is to using electric field by applying using a scanning PFM tip. So this 4 little movies shows what we got using a tip. So for this one, we place a tip at the center of the system, and starting from a upward polar system. And we can see at the final state, it will give you the opposite way, the 3 downward polarization. And they have the patterns along different directions. They have this twinning with like 120 degree symmetries. And when the tip is scanning, because experimentally the tip is always moving, and depending on the moving direction of the tip, we can actually filter out one type of the domain structures, as in this case. For example, when the tip is moving from left to right, the remaining domain structure would be the domain structure behind the tip moving direction. It's like the trailing field effect. If you move the other way, the other 2 twinning variants will remain. So which means we can think of, if we have a tip scanning back and forth, we can actually create one single band domain structures out of the 3 band. So I make an analogy with like a hair comb, that when you comb your hair, you can make them align nicely to get a domain structure like this. And for this up and down case, so when you move back and forth, actually you can screen out these 2 types of domain structures. So that's the first way. The second way we're thinking is to control the electric boundary condition by slightly reduce the surface screening charges. So we can start from this is the 3 downward polarization state. And by reducing the degree of the surface charging, surface screening, we can gradually get a very beautiful 6-domain variant state with a nicely ordering. And I'm thinking of this like a hair dryer that to clean out the hydroxyl, the protons on the film surface and create a new type of domain structures. And if we look closely at these beautiful domain structures, we can see it's like a highly hierarchical self-similar domain structures, because locally we have this twinning of type 2 twinning with up and down polarization, and a combination of the two forms a larger domains. And moreover, a combination of these 2 levels of domain give you a even larger twinning structure. So it's like a domain within domains. And which means if we starting from an S-grown system with this kind of messy domain structures, we can use the Pauling electric field to create a polar, three variance polar structures and switching them back and forth. And by using the hair comp technique to control the scanning tip directions, we can get either these 2 variant polar structures or these 1-band 3 polar structures. And also by controlling the surface screening charges, we can get new domain structures with several levels of twinnings. And also if you start from here, we can get another type of 3 variant non-polar systems. And the remaining thing we're still wondering is that if we can starting from a 3-polar system to get this 3 non-polar system by just using the scanning tip and by applying the mechanical force and the electric bias all together. So that's the thing we're still working on. And this is the first example on PTO systems. Another thing is we also tried the similar setups, but with the barium titanate materials. And what we got is also quite fascinating. So I have a 1-page introduction about the supercrystals in ferroelectrics. So there has been a few reports on the supercrystals. So by supercrystals, people usually means there are 2-dimensional, 3-dimensional periodicity that's beyond the crystal lattice. So for example, in this case, they create a composite ferroelectrics by doping other elements to the lithium niobate in a periodic way, and they use the diffraction technique, and they saw this pattern that's a feature for usually for the crystals. But this lattice constant for this microscopic crystal is like micro scale. Another very classic example is the observation of the polar vortex arrays or lattices in the superlattice systems. So in this case, this supercrystal is like the periodicity between the polar vortices. And more recently, one of our collaboration work is the discovery of a supercrystal state also in this superlattice system, but which is stimulated by ultra-fast laser pump. And this will, in this case, the periodicities between these actually is nano-sized AC domain structures. So what if, so you can see all of these cases, they are either they are superlattice and with heterogeneous interfaces or some artificially created periodicity. What if I tell you that we have predict the supercrystal exists just in a very simple thin film case? So here is what we got using this kind of thermodynamic state, but for the barium titanate systems, we're starting from randomness without any periodicity of the noise, but what we end up with is this nicely intertwined patterns. And if we look closely, these intertwined patterns, they are consisting of either the tetragonal polarization orientation, which is the orange, purple, and gray, and also at the junction between them is kind of orthorhombic polarization directions. So you can think of this like a unit cell of these 2D supercrystals with the orthorhombic four corners as the lattice point of this unit cell. Oh, okay, yes, it's on my last page. And what makes things more interesting is that without changing these domain polarization directions, with the other two energetically degenerate systems, here is just a change of the volume fraction between these tetragonal states. So in this case, the orange one is the dominant one. Here's the gray one, here's the purple one. So all of them, they show this intertwined 2D periodicity. And these are kind of preliminary results from us, and we're looking deep into the local polarization configuration and other switching properties of these systems. And we are also anticipating there would be discovery in experiments that this supercrystal system really exists. So I'll sum up my presentation. So we have generated many nicely domain structures purely from phase field modeling and starting from a randomness. And they are most of them, they have been observed in experiments. Well, this one is more interesting, and we have seen it is stabilized under open circuit condition for the PTO 111 oriented thin films. For the barium titanate, we predict another type of supercrystal with 2D periodicity domain structures. And we hope these two predictions will be validated from experience in the near future. Okay, I'll end up here, and thank you for your attention.
Do you have any questions?
Thanks. Thank you for the talk. In your barium titanate film, 111oriented, you predict that there will also be some charged domain walls. Have you done any measurements yet on them? Because the signal at the surface should be quite distinctive. You've got some head-to-head polarizations you showed. Yeah.
So most of the cases I show here, they are not charged domain walls. But indeed, there are very locally charged domain walls, especially in this case. You can see there's a head-to-head configuration in this supercrystal state, but not in the previous lead titanate state.
Okay.
Very nice. For the lead titanate, for the six-fold one that you showed at the end, with your hair dryer idea, for an experimental perspective, would that mean I should thin down the bottom electrode till it's almost not screening it perfectly? How experimentally should we accomplish this?
Okay, so for the bottom electrode, for all my simulation, I assume it's grounded. So what we tune is just a surface electric boundary condition. So experimentally, I'm thinking to make it into a ultra vacuum state to leave out the surface screening.
Okay, I think we'll have to postpone any more discussion for lunch, but let's thank Bo and the rest of the speakers in this session.